Alright everyone, so we're going to try and get through a Zener diode lab while we're away from campus. I pulled up just a quick information sheet that I have. Basically the Zener diode is a power regulator or a voltage regulator when connected in parallel to a load. Right here we see the step-down transformer that goes to the bridge rectifier. Okay, the bridge rectifier is converting AC into DC, as we've learned previously. Outside of the bridge rectifier, we see all DC, positive and negative DC voltage buses. The smoothing or capacitor filter is there to help maintain that good quality of DC, although for the lab we do use a power supply for one of the parts. And then we have the current limiting resistor, which is used to help dissipate power for the Zener diode. And not allow it to become a short circuit. And the Zener diode is connected in reverse bias with the negative to the negative DC voltage bus and the positive to the positive DC voltage bus. So now we're going to take a look at the lab. So the objective of this lab is to construct a circuit that's going to test the functionality of the Zener diode. The first thing that it has you look at is the Zener diode in a series circuit with the 100 ohm resistor. And we're going to slowly increase the power supply or the voltage to the actual circuit. Right here we have an ammeter, we have our 100 ohm resistor, and then we have our Zener diode connected in reverse bias. You can see here how the anode side is connected to the negative supply. The cathode side is connected to the positive supply. Keep in mind, this is a special purpose diode that's designed to be used in reverse bias. They typically have design voltages ranging from 5 to 12, sometimes higher in voltage. And mainly their biggest attribute is the ability to dissipate their own power, although it is limited. You can see here, however, you should not exceed the maximum Zener current of 190 milliamps or the diode will short out. Okay, for the first portion in the series circuit with the diode in reverse bias, we're going to slowly increase our supply voltage from 0 all the way to 30 volts, which is our maximum power supply voltage. So we've filled out the top portion of this, and you guys are responsible for filling in the bottom portion as part of your lab. For the top portion, what we're seeing here is no voltage is being dropped at the limiting resistor, VRLIM. Okay, I simulated, or I gave an example here, how it will start to drop a small voltage before it reaches its design voltage of 12. But before it does so, there will be some small leakage current that you might measure. Once it gets to its design voltage of 12 volts, the Zener diode will continue to drop 12 volts. So down here, you would say that the Zener diode continues to drop 12 volts. While the rest of the remaining voltage of the 16 volts will be dropped across the current limiting resistor. So we should see about 4 volts drop there. Since current flow is dictated by the current limiting resistor, we would go to our calculator. Okay, we would take 4 volts, divide that by 100, and we would see approximately 40 milliamps. So you should do those steps for the following 17 through 30 volt calculations. Okay, down here I put a small note to help you get through that. If you're having trouble with that, just please try your best, and we'll sort it out in class when we get back in the in-person course. Here I have a small graph created that helps understand how the Zener diode works in reverse bias. So on the left-hand side, we're actually seeing a negative voltage applied to the anode side of the diode. Current flow will not be allowed until we start to approach that Zener voltage. Here, we're seeing that we get a small current flow of about 0.2 amps. Again, not terribly accurate. But once we get to 12, it starts to do what's called avalanche. So the avalanche means that it's going to allow current to flow until it reaches its breaking point. The next portion of the lab in Procedure B, we're actually going to use the Zener diode as the voltage regulator. What we're going to see here is when we have an undervoltage on the circuit, the Zener diode is not able to regulate voltage as well as it would if we were at the actual voltage or high enough voltage for the Zener to be at its design voltage of 12 volts. So we have two ammeters in the circuit, A1 and A2. A1 is going to be total current flow for the circuit since it is in series with both loads. A2 is only going to see the current flow through the resistive load. The resistive load should be regulated by the 12 volt Zener diode for this example. The 12 volt Zener diode will also experience some current flow. That will be calculated taking A1 and A2 and subtracting those values to get the Zener current flow. Another thing that you should try and calculate on your own is how much power is actually being dissipated by the Zener diode. That's a big thing for Zeners, as they usually are experiencing some kind of current flow and need to dissipate power. Overall, what we're really looking at for this circuit is the Zener diode will continue to regulate voltage to a certain point. While it does really well with the 15, 20, and 25 volt supply voltages, once it gets to the 30 volt region, it starts to diminish its voltage control a little bit. So at the resistive load, we might not see exactly 12. We might see 12 and a half or up to 13. Okay, so that's what we're seeing down there. As far as the calculations for calculating Zener current, we're going to take A1 and A2, or current flow 1 and current flow 2, subtract those values from each other, and that will give you the anticipated amount of current flow through the Zener diode. Down below, you should replicate the graph that I have provided above. Keep in mind that this graph is actually upside down, so this is the bottom left quadrant of the graph. Assuming that the Zener diode is in reverse bias, it would see zero current flow from this region to about the 12 volt mark, and you could do your best to size this graph appropriately. Then once we reach about the 12 volt mark, we should see exponential current flow again until it was exceeded to 190 milliamps, and then it would short out. A couple other points to ponder that you should include in your lab report. So what happened to VZ and IZ when the voltage supply was changed from 0 to Vmax? You should note that in the graph above. It was a slow change. It was a slow change from no current flow to full current flow. So we should see 0 amps up to a certain point. Then we'll see a small leakage current. And then once we approach that design voltage of 12, we're going to see exponential current flow. Okay, a couple other things to consider. What happened to the voltage across R lim when the supply voltage is changed? So the current limiting resistor is responsible for dissipating any voltage that is not handled by the diode, which is the Zener diode that's regulating voltage to the load. So if the Zener diode was capable of keeping 12 volts to the load, out of 20 volts, let's say, the remaining voltage would then drop across the current limiting resistor of R lim. How is the voltage just distributed across the various circuit elements? Well, we saw that the resistors are in series, so source voltage equals the sum of those voltage drops. Since the Zener diode is in parallel to the current limiting resistor, or the resistive load rather, that had the same amount of voltage drop as the resistive load. Next, how is the Zener connected for normal operation as a voltage regulator? It was connected in reverse bias and in parallel to the load. How did the operation of the Zener affect the voltage across the load? So the Zener, by regulating voltage drop across itself, will help regulate voltage to the load in parallel with it. What does the operation of the Zener affect the current through the load at the Zener? How does the operation of the Zener affect the current to the load and the Zener? So by regulating voltage, we're trying to maintain a consistent current flow, and we can see that in the second data table. You'll notice that once we do start to regulate that 12 volts of the Zener, we get a pretty consistent 48 milliamps through the resistive load, measured by A2, until we reach a point where there's too much voltage for the Zener to handle. The next thing that we're going to look at for our labs is how we actually use a transistor in conjunction with a Zener diode to create a full voltage regulator. Thanks for watching.